So in today's lesson, we're going to be talking about forces. This is our introductory lesson into our forces unit. So we'll be covering some basic terminology and concepts. So make sure to pay attention and reach out if you have any questions. So let's just start with talking about forces that you experience in your life, right? What are some forces that you can think about that you've experienced? So I would suggest that probably what comes to mind first is the force of gravity. That tends to be the first example that people think about. Of course, that is one type of force, but we're going to be exploring many others as we work through today's lesson. So generally speaking, we would say that a force is a push or a pull, or you could think of it also as a twist, right? And so we can think about those forces where we're pushing and forces where we're pulling. So let's move on and talk about types of forces. So we can categorize forces into four large categories. And so the first is what we call gravitational, and this is the one that you're likely to be familiar with, but we're going to expand upon what your current understanding is. So gravitational force is a force of attraction between all objects. We tend to think of the force of gravity as being that force that, if we're close to the surface of the Earth, pulls us towards Earth. But in actuality, all bodies experience gravitational forces. It's just that most of those bodies don't have enough mass to exert a whole lot of force, whereas the planet Earth has an immense mass and therefore exerts larger gravitational forces. So that's the first one, gravitational forces. The next one is electromagnetic. And so this is the force caused by electrical charges. And so you will hopefully remember from grade 9 science, learning about electricity and charges. We know that negative charges like to repel other negative charges, positive charges like to repel other positive charges, and then oppositely charged particles will attract each other, right? So that is a force, that repulsive force or that attractive force. Next, we have strong nuclear. And this one is, I wanted to have the visual here to help you make sense of it. So, again, in grade 9, you would have talked in depth about the structure of the atom. And you'll remember that in the center of the atom is the nucleus, and that the nucleus is comprised of both neutrons and protons, right? And so we know that protons have the same charge, and so there are some repulsive forces there. And so why is it that the nucleus doesn't kind of just blow apart, right? And so we attribute the fact that it doesn't blow apart to some strong nuclear forces that hold those protons and neutrons together in the nucleus, despite repulsive factors. And lastly, we have weak nuclear forces. And so weak nuclear forces are those forces that are responsible for interactions involving subatomic particles. So we will touch on this a little bit this year when we discuss nuclear reactions, right? And one such example is beta decay. Okay, so those are just, what is going on when we take small particles and interact them. Okay, so I thought it would be a useful exercise at this point for you to take a look at those four forces and maybe on your whiteboard jot down the order of strength of those forces, what you perceive or what you would be your best guess as to which of those four forces would be the strongest and which would be the weakest. So pause the video and with a partner, take a minute to do that. Okay, so let's take a look. So this is a table that's pulled from your Nelson textbook, and it basically describes the relative strength of these four fundamental forces that we've talked about. So let's see how you did. It's interesting because often people will think that gravity is one of the stronger forces, but in fact it's that gravitational force is much weaker than the other three forces, on the order of 10 to the power of 36. So if you guess strong nuclear would have to be the strongest, then you guessed right. I mean, that is what's holding, atoms together, so all matter together. That's pretty significant, right? Electromagnetic has to do with attraction of charges as well. So that's going to be on a very large order. We have weak nuclear, and just to help you understand, if we think of this as a ratio, the ratio of strong nuclear to gravitational would be 10 to the power of 38 to 1. That is a significant difference. Okay, let's keep going. So there are some other super important terms for us to understand as we navigate through this unit. So the first one is the normal force. Super important for you to understand the concept of the normal force. And you may remember from our optics unit in grade 10 where we talked about the normal line in an optics diagram. And so a normal line is simply a line drawn at a 90-degree angle to the surface. And so that is the same idea as we have here, except we're not talking about a line, we're talking about a force and the direction that it acts in. Okay, so for instance, let's say I had just a pen resting on some kind of horizontal surface here. Then that pen, I know, it's not sinking into that table and it's not floating above the table. It is staying, it is at rest. And so what that indicates to me is that the force of gravity, which is acting downward towards the surface of the earth on that pen, must be equal but in opposite direction to the normal force here. And the normal force, if my pen is sitting along this surface, then 90 degrees to that surface would be the normal force. And so because those are equal, we see that that object is at rest in this case. If, however, I were talking about a snowboarder accelerating down a hill, the normal force is not directly opposite gravity. Of course, we know gravity just acts down, right? It acts down, but our normal force here is going to be on an incline, sort of off in that direction and perpendicular to the surface that the object is traveling on, or the object in motion is sitting on. Okay, so that's important to remember. Now, we're going to talk about friction next. So friction is, I think you have a conceptual idea about what that is. We know that when two objects slide past each other, what can slow the object down on a surface is friction, and friction works sort of opposite the motion, right? So if you're trying to move an object, say, to the right, then friction is actually acting in towards the left. It is opposing that motion. If we were to zoom in on those two surfaces, we would see that, unless it's an absolutely ideal surfaces, there are going to be some bumps and some ridges here. And when those two surfaces interact, that's going to cause that slowdown. So that's friction. So just remember again that friction is acting in opposite direction of motion or even attempted motion. Okay, next we have tension, right? So tension, typically we think about in, ropes and cables and things of that sort, right? So this individual here is pulling that rope, so the rope is feeling tension in the opposite direction. In the same way, this pulley, which is aiming to lift this box, is having a couple forces act on it. It's having the force of gravity, which is acting downward, and so that rope is going to experience tension in an upward fashion as a result of the opposing force of gravity there. All right, we're going to see a lot more about tension in the coming couple of weeks, so stay tuned. So I wanted to talk to you about contact forces versus at a distance forces. So contact forces are forces that are going to result from direct contact, as they suggest. So for example, pushing a box, your hand is on the box, and so the force that's pushing the box is in direct contact with the box itself. There's a force at a distance where there's no actual physical contact between the body that is in motion and the force that's acting on it. And so a great example of that is the force of gravity. So I want to talk about measuring force, and so you should know that force is a vector quantity. It has magnitude and direction. And so we talk about Sir Isaac Newton. You've probably heard of Sir Isaac Newton. I'm going to pull up a photo in a minute here. Try to guess what he looks like. He was, an individual who did a lot of studies and experiments in the world of physics. And so, as an homage to him, we call the unit that we use for force is the Newton. Okay, and we use the capital letter N to represent that. So in the lab, we're going to be doing some experiments with forces, and we're going to be using a spring scale, possibly I don't know if we have a force sensor, but we do have a spring scale, and if you fish, you may have something similar to find the mass of the fish that you've caught. But this device is a pretty simple device that will help us to measure forces on objects. All right, so we need to talk about something called a free body diagram. And we've talked about this a lot, I think, in our course about how important it is for us to create a beautiful diagram to help us to visualize the problem at hand. And then we can sort of make sense of it a little bit better. Now, I can't stress enough how important in our forces unit, how important it is to draw a free body diagram. Without further ado, let's get into it. So we have two types. I've talked about the free body diagram, but before that, we have a systems diagram. And really, that's just a sketch of all the objects that might be in a situation. Whereas a free body diagram is like a simple diagram showing only the object being analyzed and all the forces acting on it. So a systems diagram is going to look like this. The systems diagram is just basically, okay, you have a physics table, a physics book on a desk, right? It's a visual representation of the scenario. Whereas a free body diagram, usually we will use a square or a rectangle to represent the object that is experiencing some forces acting on it. And what we do is we will write out vectors in the direction that the forces might be acting. So for example, if we consider this physics book being pushed across a table, then we can think about the forces that are acting on that textbook. For sure, we would say that, I know that that textbook is not rising or falling into the table. So I know that I have a force, normal force, that is going to be acting perpendicular to the surface of the table, and the force of gravity acting downward, right? And then those are likely to be equivalent if this book is being pushed horizontally. And so I know that there's the applied force. So this capital A here is meant to indicate applied force acting in that direction of motion, and that the force of friction is going to be acting in opposition to that motion. Okay, so again, free body diagram, just a simple, I'm not an artist. I really like these free body diagrams because they're usually just rectangular shapes used to depict an object experiencing forces, and then the vectors to depict the types of and direction of the forces acting on the object in motion. Okay, so I'm going to switch to my Jamboard, and we can get started with some examples here. So give me a moment. Okay, so here is an example of a question you may get, or this may be one of the building blocks in one of the problems that you're attempting to solve. So it says draw a free body diagram, and you'll often see me just say FBD for each of the following. And so here is our first example. And so we have a box. In that box, it looks like it has is being sort of pulled by a rope in this direction towards the right. So pause the video, try to draw out a free body diagram either on your whiteboard or in your notes to represent this object, and then resume the video when you're ready. Okay, so I'm going to start by first going ahead and drawing a rectangle to represent the box that's being pulled, the trunk. And so I'm going to analyze the situation. I can see that this trunk is on a horizontal surface, And so I know that because of that, it's going to be experiencing the force of gravity acting downward, right? And it's also going to be experiencing a normal force that is directly opposite to that. Now, I also know that is being pulled, and so there is absolutely an applied force acting on this trunk. And I'm going to assume that this is not a frictionless surface, and so there is likely to be a force of friction acting opposite the motion as well. So I hope you did okay with that. Let's move on to a second question, or a second example. And so in this example, we have a coffee cup that is resting on a horizontal surface. So pause the video and draw what you believe to be the free body diagram for this coffee cup. All right, I'm going to go ahead and do this. So I'm again going to draw a rectangular type shape to represent the coffee cup. And I know that this coffee cup is just at rest. So the sum of all of the forces acting on it must be zero. Otherwise, it would be in motion. Well, it's sitting on the table, and so it must be experiencing the force of gravity. And it's also experiencing that normal force. And those would be equal but opposite in direction, equal magnitude, opposite direction, to allow that coffee cup to sort of just sit there. All right, let's keep going. All right, and so in this scenario, we have an individual baseball player who looks like they're sliding into one of the bases, and they're sliding in. Yeah, that's pretty much it. So I want you to imagine what has to be happening here in order for them to reach that base. And so I want you to pause the video and draw your FBD. Okay, so when I consider this situation, I'm going to say, well, this person is going to be slowing down and eventually stopping. So there's no external force on this person except for the force that is acting to slow them down, as well as the normal and gravitational forces. So the vertical forces are going to cancel each other out. We have the normal force, which is in this case just the ground, and we have the force of gravity keeping her on the surface of the earth. But we also know that there is friction that is acting to slow this person down. Now remember, if the motion is in this direction, then friction has to be acting in the opposite direction to the motion. Hopefully you did okay with that. And if not, make sure to reach out with questions. All right, let's look at the next example. So here we have looks like a tennis ball to me, and that tennis ball looks like it is intended to be shown in free fall, just sort of falling towards the surface of the earth. So take a minute to draw a free body diagram. Okay, so I am going to take this up. So again, it doesn't matter that it's a ball. You could draw it as a ball, but most often we see people drawing squares or rectangles. Now, in this case, we kind of can there's some things we may want to assume here, right? I know that there are no horizontal forces acting on this, and that's an assumption I'm making. It doesn't look to be going sideways in any direction, but I know that it's in free fall under the force of gravity. Now, I know in this case there is no normal force because it's not sitting on a surface, right? There's no surface for the normal force to be acting on. But one thing you may have thought to include, which is reasonable to include, is that you may be thinking about the force of air resistance acting opposite that tennis ball's motion, which is a fair assumption to make on planet Earth. All right, we're getting to the last examples here. So I'd like for you to draw an FBD for this situation. Now, I mean, I think it all depends on what you consider to be happening here. I think what is intended to give you some a little bit of frame of reference. I think that this young lad is pulling the wagon in this direction using the rope, and I think that this young person may be pushing it as well in the forward direction. So, or we don't know, but let's just assume that that person is pushing in that direction. All right, so go ahead and draw your free body diagram. Okay, I'm going to take this up. Now again, if you interpreted something different from this diagram, then that would impact what you write. But in this case, we have a wagon being pulled on a horizontal surface. So again, we see the force of gravity being countered by that normal force. So no net force in the vertical direction. And we see this young person who seems to be applying a force to pull it forward. And we also see another young person applying a force. And so I'm going to differentiate between the one person and the second person by indicating a first and a second applied force. Now, we also can assume that there is likely to be a force of friction acting on the wagon opposite the motion. Okay, one last example. So here we have a skier that is on an incline going downhill on a slope. So take a minute to draw your FBD. All right, let's go. So often when you see an object on an incline, in the free body diagram, you'll also draw in that incline. Not always, but I like to. It just reminds me of the perspective. And so I'm going to draw my object as the square or rectangular shape on the incline. So I'm going to use, because this is a little bit more complicated of a diagram, I'm going to draw in some of the forces. So I know for sure there is the force of gravity acting downward. Now, the force of gravity does not act opposite the normal force always. My normal force, you'll remember, is going to act perpendicular to the surface. And since the surface is right here, my normal force is going to act perpendicular to the surface. Now, what's actually causing this person to move downhill is a component of the gravitational force. And, in grade 12, you'll look at, well, how can we separate gravity into components to show the downward motion down the hill? But we can save that for another day. Now, we also should draw in the likely force of friction, which is going to slow this skier down by opposing its motion. So hopefully you did okay with that. Those are our free body diagrams. I'm going to give you some homework to practice this, but we have one small little piece to this lesson to go. And so if we're looking at forces and we want to calculate the net force on an object, okay, when I say net force, I mean the sum of all forces, right? And since forces have a magnitude and direction, we know they're vector quantities. And so we're going to simply add all of the vectors. We're going to combine vectors to get the overall or net force on an object. So let me show you what I mean by this. So here I have a free body diagram, and it looks like the drawing is indicating that I have 7 newtons upward and 3 newtons down, and I have 4 newtons to the right, and then 9 newtons to the left. And so it's my preference to talk about the forces in terms of, up and down and left and right in this. And so I'm going to sum up the the vertical and I'm going to sum up the horizontal. So the forces in the y direction are going to be 7 newtons up plus 3 newtons down. Of course, we're going to make those directions the same in order to be able to combine them. Right? Negative up is equal to positive down. And so that, and this is a step that I'm showing explicitly here. This is a step you could probably skip in your own work. And so that gives me 4 newtons up. And the forces in my x direction are, of course, going to be 9 newtons to the left and 4 newtons to the right. And so I'm going to say that overall that is 5 newtons to the left. Okay. And so in order to find my resultant force, which I'm going to call F net, I'm going to use Pythagorean theorem, okay? Because remember that I have, overall, I have 4 newtons up, and I have 5 newtons, oops, undo that, and then I have 5 newtons to the left. Right? And so I know that, let me just get rid of this here, this 4 newtons here, and I'll rewrite it on the other side. And I know that my resultant is going to be, essentially in this direction. And so using Pythagorean theorem, I know that my net force is going to be the square root of 5 squared plus 4 squared, which is approximately, well, I only have one significant digit here, so I'm going to say 6 newtons. So my net force is 6 newtons. I still need an angle here, so I'm going to use, my opposite and adjacent sides and say that theta is equal to tan to the negative 1 of 5 over 4, which is approximately 51 degrees. Rounding that to one significant digit would give me 50 degrees. And so my net force, I would say, is 6 newtons, 50 degrees. This is a little awkward, isn't it? Maybe we can say 50 degrees from the vertical. And there we have it. Okay, and so I am going to point you in the direction of some practice work, some work that you should do to firm up these skills and to revisit these concepts tonight at home, just to kind of strengthen those neural pathways. But be sure to reach out if you have any need for some help.